Yes, ma'am.
Yeah. So today's topic we will be dealing is production of antibiotics. We will concentrate on the production of 3 different antibiotics, which is there in your syllabi: penicillin, streptomycin, and tetracycline. I repeat, production of antibiotics: penicillin, streptomycin, and of course tetracycline. So what are antibiotics? Antibiotics are antimicrobial agents. They are secondary metabolites produced naturally by microorganisms, usually fungi or bacteria, that inhibits other microorganisms. You just look into the word antibiotics. Anti means against, biotic means life. So antibiotics are antimicrobial substances. They are secondary metabolites. Primary metabolites are those that are involved in the metabolism of an organism for its growth and multiplication. The secondary metabolites are additional substances produced by various, all microorganisms will not be having the capacity to produce antibiotic, but there are few organisms that produces antibiotic as its secondary metabolite. They are produced either by fungi or bacteria, and when produced, it will inhibit the other group of microorganisms. I repeat again, antibiotics are antimicrobial agents, secondary metabolites produced naturally by microorganisms, usually fungi or bacteria, that inhibits other microbes. The first antibiotic was discovered by Alexander Fleming in the year 1928 from the filamentous fungus Penicillium notatum. So Alexander Fleming, going to the history of antibiotics in the year 1928, he isolated the antibiotic penicillin from the filamentous fungus Penicillium notatum. He found Penicillium notatum as a fungi. It was an accidental identification or an accidental discovery in the place where Penicillium notatum grew as an contaminant. So the first antibiotic was discovered by Alexander Fleming in 1928 from the filamentous fungus Penicillium notatum. The antibiotic substance named penicillin was not purified until the 1940s, which was carried out by Flore and Chain, just in time to be used at the end of Second World War. So antibiotic penicillin was commercially synthesized to be used in the end of Second World War by Flore and Chain, nearly around 1940s. So very recently, if you see, we have various antibiotics that are produced commercially. So if you look into this table, you have on the left hand, the table with the left and right. Left hand, you can see the different types of antibiotics produced. On the right hand side, you can see the producing microorganism or the producing strain. So I just read the list out. Bacitracin produced from Bacillus licheniformis. It is endospore forming bacteria. Cephalosporin by Cephalosporium species. Cycloheximide by Streptomyces gracius. And F stands for fungi, A stands for actinomycetes, EFB stands for endospore forming bacteria. Cyclocerin is produced by Streptomyces orchidaceus. Erythromycin produced by Streptomyces erythraeus. Griseofulvin produced by Penicillium griseofulvum. Kanamycin produced by Streptomyces kanamyceticus. Lincomycin produced by Streptomyces lincolnensis. Neomycin produced by Streptomyces frediae. Nystatin produced by Streptomyces norsii. Penicillin produced by Penicillium chrysogenum. Polymyxin B produced by Bacillus polymixa. Streptomycin produced by Streptomycin gracius, and tetracycline produced from Streptomyces ramosus. So there are endospore forming bacteria, fungi and actinomycetes that are involved in commercial production of different antibiotics industrially. So as far as your syllabus is concerned, we will concentrate on the production of penicillin by Penicillium chrysogenum, streptomycin from Streptomyces gracius, and of course tetracycline from Streptomyces ramosus. Streptomycin and tetracycline are produced from the strains of actinomycetes, while penicillin is produced by fungi. So of course we require something called as a bioreactor or a fermenter. All these antibiotics are produced by submerged aerobic fermentation methods, which means a feedback mechanism method. You will collect and you will feed. It is not batch fermentation. You will feed each time to produce the end product. So the employed technique for the production of antibiotic, if you see, production of penicillin, streptomycin and tetracycline is submerged aerobic fermentation because it requires aeration. It requires oxygen. It is submerged inside the medium and fermentation is going to be carried out. So aerobic submerged fermentation or submerged aerobic fermentation is the method employed for production of all these three different antibiotics using a bioreactor or a fermenter. The first antibiotic we will deal with is the production of antibiotic penicillin. Penicillin was the first important commercial product produced by aerobic submerged fermentation. Before the production of streptomycin and tetracycline, the first antibiotic produced using aerobic submerged fermentation is penicillin. When penicillin was first made at the end of the Second World War using the fungus Penicillium notatum, the process made only 1 milligram per decimeter of your fermenter vessel size. So the production of penicillin from Penicillium notatum is comparatively lesser than Penicillium chrysogenum. But unavoidably, the organism that was used for the production of penicillin was Penicillium notatum. So when penicillin was first made at the end of the Second World War using the fungus Penicillium notatum, the process made 1 mg Dm power minus 3 of penicillin. Today, using a different species, that is Penicillium chrysogenum, a better extraction procedures that yield is, of course, the yield is around 50 grams per Dm power minus 3. So initially, if you see, Penicillium notatum was used, and very recently, and high yielding strains of Penicillium chrysogenum is used for the industrial production of penicillin. What are penicillins? They are antibiotics which are produced from fungus Penicillium chrysogenum, which is a secondary metabolite produced from Penicillium chrysogenum. There are 2 different types, natural penicillin and of course semi-synthetic penicillin, including penicillin G, penicillin V, ampicillin, amoxicillin and methicillin. The antibiotic inhibits cell wall synthesis and they have bactericidal action, which means it will kill bacteria. So they are narrow spectrum antibiotic, which means they are active against a few range of microorganisms, that is gram positive, while they have only little effect on gram negative cells. I repeat, penicillin of 2 different types, natural and semi-synthetic penicillin, penicillin G, penicillin V, ampicillin, amoxicillin and methicillin. Antibiotic that inhibits cell wall synthesis. They are bactericidal in action. They are narrow spectrum drug that is active against gram positive organisms while it has little effect on gram negative cells. It has 2-ring structure and they are called as beta-lactam drugs. So if you look into the structure of penicillin, it is made up of 2 rings. The first ring we have is thiazolidin ring, and the next one we have is the beta-lactam ring. So this structure will give you the general structure of penicillin. You have something on the left-hand side on the top, acyl side chain. There is something designated as R. From natural penicillin, if you change the R group chemically or synthetically, you get something called as semi-synthetic penicillin. So when the R group of the acyl side chain is changed, you will get semi-synthetic penicillin that can be derived from what is called as natural penicillin. So penicillin, of course, the 2-ring structure. It is made up of thiazolidin ring and of course beta-lactam ring. They are also referred to as beta-lactam drugs. Regarding the biosynthesis of penicillin by Penicillium chrysogenum, as I told you, this pathway is not important as such for any organisms, but when they are producing or the producing strain of penicillin, they have to go secondary metabolic pathway for the synthesis of or for the biosynthesis of penicillin, and the pathway goes like this: L-alpha amino adipic acid in the presence of L-cysteine is converted to L-alpha amino adenyl cysteine. In the presence of L-valine, it gives you alpha L-amino adenyl cysteine valine, that is a tripeptide. With the help of enzyme cyclase, it is converted to isopenicillin N, and in the presence of acyltransferase, you get what is called as the natural penicillin, penicillin G, and of course phenyl acetyl-CoA is converted to alpha amino adipic acid, and of course the release of coenzyme A. So this pathway is a secondary metabolic pathway for the production of penicillin, a biosynthetic pathway for the production of penicillin from the organism or by the organism Penicillium chrysogenum. So industrial production of antibiotics. Before we go with the industrial production of penicillin, industrial production is basically into two different processes. The number one is upstream processing, and number two is downstream processing. So upstream processing are the methods involved in development, exploration and production. Downstream processes recovering a product. So that is how we divide the stages of industrial production. The first one is upstream processing and the second one is downstream processing. So industrial production of penicillin again. The industrial production of penicillin was broadly classified into two processes, namely upstream processing. Upstream processing encompasses any technology that leads to the synthesis of a product. Upstream includes the exploration, development and production of substances. Downstream processing, the extraction and purification of a biotechnological product from fermentation is of course referred to as downstream processing. The methods employed until production will come into upstream processing. Recovery stage or the final product harvesting stage will come into what is called as downstream processing, a very important 2-mark question. So to produce penicillin, you should supply raw materials, or what you require is called as a production medium. So production medium will contain a carbon source, nitrogen source and of course mineral source. The organism, when it is supplied with these sources, produces penicillin as a secondary metabolite. So raw material used for penicillin production, regarding the carbon source, lactose acts as a very satisfactory carbon compound provided that it is used in a concentration of 6%. So 6% of lactose is required. Otherwise, in case if you do not have a lactose substitute, you can also go in for glucose and sucrose. So sucrose and glucose can also be used in case if you are not using lactose, but satisfaction will be obtained in case if you use lactose around 6%. Regarding nitrogen sources, you have Consteep liqueur, which is written as CSL. Ammonium sulfate and ammonium acetate can be used as nitrogenous sources. So nitrogen sources is supplied by Consteep liqueur, ammonium sulfate and ammonium acetate. Regarding mineral sources, minerals are often required by the organisms for its growth. The elements namely potassium, phosphorus, magnesium, sulfur, zinc and copper are essential for penicillin production. Calcium can be added in the form of chalk to counter the natural acidity of Consteep liqueur. Consteep liqueur will give rise to acidity. To compensate it, you will use calcium in the form of chalk. And of course, precursor is required. What is an initiator is required? The phenyl acetic acid, which is written as PAA. PAA is the precursor of production of penicillin. I repeat, carbon source, lactose 6%. Nitrogen source is produced by Consteep liqueur, ammonium sulfate and ammonium acetate. Regarding mineral source, elements Potassium, phosphorus, magnesium, sulfur, zinc, and copper are essential. Calcium supplied in the form of chalk to compensate the natural acidity of CSL, and of course precursor that is used for the production of penicillin is phenolic acetic acid. What are the methods involved in the production process? It is aerobic submerged process and of course fed batch fermentation. The inoculum that is used for the production of penicillin is the spores of Penicillium chrysogenum. So Penicillium chrysogenum is used for the production of penicillin. The aeration rate, as I told you, it is submerged aerobic fermentation, so it requires air to be supplied. So aeration rate, if you see, is 0.5 to 1 vessel volume per minute. The VVM designates for vessel volume per minute. The pH required for the production is 6.5. Optimum temperature is 25 to 27 degrees Celsius, and the duration to synthesize penicillin is 4 days. The penicillin production phase can be extended to 150 to 180 hours. So I repeat, regarding production process, it is aerobic submerged process, fed batch fermentation. Inoculum is spores of Penicillium chrysogenum. The aeration rate is 0.5 to 1 VDM, pH 6.5. Optimum temperature is 25 degrees Celsius to 27 degrees Celsius. Duration is 4 days, can be extended to 150 to 180 hours. Regarding its recovery, penicillin is recovered by using solvent N-butyl acetate or methyl ketone. Extraction, which is carried out at low temperature, that is less than 10 degrees Celsius with an acidic pH less than 3.0. Penicillin containing solvent is treated with activated carbon to remove impurities. Addition of potassium or sodium acetate salts are used to precipitate penicillin. So penicillin during the recovery, it will be mixed with the solvent and extracted at low temperature. The impurities are removed using activated carbon. To precipitate penicillin, you will use potassium or sodium acetate salt. I repeat the production process again. Aerobic submerged process, fed batch fermentation, inoculum, spores of Penicillium chrysogenum, aeration rate 0.5 to 1 VVM, pH 6.5, optimum temperature 25 degrees Celsius to 27 degrees Celsius, duration 4 days. Recovery, penicillin is recovered by using solvent N-butyl acetate or methyl ketone. Extraction is carried out at low temperature less than 10 degrees Celsius and an acidic pH less than 3. Penicillin containing solvent is treated with activated carbon to remove impurities. Addition of potassium or sodium acetate salts are used to precipitate penicillin. So if you go into this picture, it will very clearly show you, it is a flow chart that shows you the process of penicillin production or penicillin fermentation. So if you have to go from the left to right, so you have lyophilized culture of Penicillium chrysogenum. You have to go in for the production of inoculum, what you call as starter culture in food microbiology. Here you will mention it as inoculum. Pre-fermentation using a pre-fermenter to make the organism produce secondary metabolite. The fermenter to bring about the entire process of fermentation. The nutrients are continuously supplied to produce penicillin. You have to filter to remove the mycelium. You have to supply it to the cooling tank before you go in for purification and recovery. So that is the process that is used for the production of penicillin. So if it is asked for 10 marks, you have to include this diagram. So this is a short form of what production of penicillin is all about. A medium of constant liquid, a byproduct of starch manufacture, yeast extract and other substrate is added to the fermenter, and this is what we call as production medium. After 40 hours, penicillin begins to be secreted by the fungus. The mold mycelium is filtered from the harvested product. Penicillin is extracted with the organic solvent, butyl acetate, in which it dissolves. Potassium salts are added and a penicillin precipitate is formed, which is washed and of course dried and is supplied in the form either of tablet or a capsule. So it depends. The next antibiotic we will go or we will deal with is streptomycin. So streptomycin production. Streptomycin was first produced by Salmon A. Waxman, who is called as father of antibiotics, in the year 1945. So 1945, Salmon A. Waxman was the first person who produced the antibiotic streptomycin, discovery of streptomycin, as to say. They are secondary metabolite of an actinomycete, Streptomyces gracious, which is an aminoglycoside antibiotic. Structurally or chemically, they are three-ring structure. They are aminoglycoside antibiotic. It is the first antibiotic used against tuberculosis, TB, and also against bacterial meningitis. So the first ever antibiotic that gave a very prompt and a good result against tubercle bacilli is streptomycin. The mode of its action, if you see, it binds to 30S ribosome and blocks protein synthesis. It is active against gram-positive and gram-negative bacteria. So they are broad spectrum antibiotic. They act both against gram-positive and gram-negative bacteria. I repeat, streptomycin was discovered in the year 1945 by Salmon A. Waxman and his co-workers cats. It is a secondary metabolite of Streptomyces gracious, which is an actinomyces. Regarding its chemical structure, they are aminoglycoside antibiotic. First antibiotic used against tuberculosis and also against bacterial meningitis. It binds to 30S ribosomes and blocks protein synthesis. They are active against gram-positive and gram-negative bacteria, so as to say they are broad-spectrum antibiotics. So regarding the chemical structure of streptomycin, the structure is three rings. It is this combination of three-ring structure. The first one is the streptodine, the second one we have is the streptose, and the third one we have is called as streptosamine. So streptodine is chemically inositol with two guanido groups. Streptose is methyl pentose and streptosamine, if you see, is N-methyl L-glucosamine. That is why it is said as aminoglycoside antibiotic. So regarding its biosynthesis, of course, it is a bypass of what is called as your glycolytic pathway. So D-glucose is converted to D-glucose 6-phosphate. You get three different products: myo-inositol 1-phosphate, D-glucose 1-phosphate, D-glucosamine 6-phosphate, and myo-inositol, if you see, is converted to 1-phosphate is converted to myo-inositol, streptidin 6-phosphate. The D-glucose 1-phosphate goes to what is called as L-dehydrostreptose 1-TDP, and of course D-glucosamine on the right hand side is converted to UDP N-methyl D-glucosamine 6-phosphate, and on the left hand side these two combine, which means streptodine 6-phosphate, L-dehydrostreptose 1-DTP combines together to give rise to 4-streptotidin 6-phosphate. On the right hand side you have N-methyl L-glucosamine with a synthesized. These two combine together to produce what is called as dihydrostreptosamine 6-phosphate. Streptomycin 6-phosphate is produced, and then it is converted to what is called as streptomycin. So it is a pathway, that is secondary metabolic pathway from D-glucose to give rise to the antibiotic streptomycin. Okay, of course, production of streptomycin, it is again aerobic submerged fermentation. You require something called as production medium. Production medium should have a carbon source, nitrogen source, and of course inorganic nitrogen salts are also supplied. So medium for the fermentation process of streptomycin production essentially comprises of carbon source. The carbon source may be dextrin, glucose, or starch. Regarding its nitrogen source, you can use cotton seed meal, soybean meal, or soy flour, or corn syrup. You have to use corn steep liquid, casein hydrolysate, and of course yeast extract. So they can give you nitrogen source. Of course, salts, minerals, pure inorganic nitrogen salts are used in the form of ammonium and ammonium nitrate. I repeat, medium for the fermentative process of streptomycin. Streptomycin production essentially comprises of carbon source, example dextrin, glucose, starch, nitrogen source, cottonseed meal, soybean meal or soy flour or corn syrup, cornstarch liquor, casein hydrolysate, yeast extract, and pure inorganic nitrogen salts, including ammonium and ammonium nitrate. The production or the fermentation of streptomycin is divided into 3 different phases: phase 1, phase 2, and phase 3. In phase 1, you can see rapid growth producing mycelial biomass, and little production of streptomycin is obtained in this phase. The second phase, if you see, additional production of mycelium is found and streptomycin accumulates in the medium in higher rate. So during the phase 2, if you see, there will be one different action. Proteolytic activity of the microbe releases ammonia to the medium from the soybean meal, causing a rise in pH. And the third phase, if you see, the process will be completed. Finally, the mycelium has to be separated by filtration and antibiotic are recovered. The glucose and ammonia released are consumed during this phase. So during the phase 3, if you see, the ammonia that is generated from phase 1 is consumed during the phase, and the pH remains fairly constant between 7.6 and 9. So I repeat, phases during fermentation of streptomycin, you have 3 different phases: phase 1, phase 2, and phase 3. Phase 1, you have rapid growth producing mycelial biomass. Little production of streptomycin is obtained. Phase 2, additional production of mycelium is seen, where streptomycin is accumulated in the medium. In phase 3, process has to be completed and it gets completed. Finally, the mycelium is separated by filtration and antibiotic is recovered. Regarding the production process, the production strain that is used for the synthesis of streptomycin is the actinomycete Streptomyces gracious. It is an aerobic submerged fermentation process, fed batch mechanism of fed batch fermentation. The temperature employed is 27 degrees Celsius to 30 degrees Celsius. pH is 6.5 to 7.5. The aeration rate, of course, it is an aerobic submerged fermentation, so you need to supply sterile air. So the aeration rate is 0.5 to 1 vessel volume per minute, VVM. Duration of fermentation, if you see, is 6 to 8 days. Regarding penicillin, I told you it is 4 days, and the duration of synthesis of streptomycin, if you see, it takes 6 to 8 days depending on the strain that produces it. Regarding the recovery, using weak cationic exchange resins in an ion exchange column can be used, chromatographic column can be used. Treatment with activated carbon is necessary in order to remove impurities, and streptomycin can be precipitated in the form of sulfate salt. I repeat, production process of streptomycin. The production strain, Streptomyces gracious, aerobic submerged fermentation, fed batch mechanism, temperature 27 degrees Celsius to 30 degrees Celsius, pH 6.5 to 7.5, aeration rate is 0.5 to 1 ppm, duration of fermentation is 6 to 8 days depending on the strain. Regarding its recovery, using weak cationic exchange resins in an ion exchange column, treatment with activated carbon is often necessary to remove impurities. Streptomycin can be precipitated in the form of sulfate salt. The next antibiotic that we will be dealing is tetracycline. Tetracycline is a drug which is 4-ring structure. So regarding tetracycline, it was discovered by Benjamin Ming-Taggart. So Benjamin Ming-Taggart made his discovery of the first tetracycline antibiotic, the chlortetracycline, which was commercially named Aureomycin at Lederle Laboratories, USA in the year 1945. These are broad-spectrum antibiotic, which means they are effective against gram-positive and gram-negative bacteria. They inhibit protein synthesis by blocking the binding of amino-acyl tRNA to ribosomes. So of course, it inhibits protein synthesis. The basic structure of tetracycline is composed of naphthalene ring, a 4-ring structure. So penicillin 2-ring, streptomycin 3-ring, tetracycline of course is 4-ring structure. I repeat, tetracycline. Benjamin McDougall made his discovery of the first tetracycline antibiotic, chlortetracycline, at Ladderley Laboratories, USA in the year 1945. They are broad-spectrum antibiotics effective against gram-positive and gram-negative bacteria, inhibits protein synthesis by blocking the binding of amino-acyl tRNA to ribosomes. The basic structure of tetracycline is composed of naphthalene ring, a 4-ring structure. So this is the general chemical structure of tetracycline. So you have tetracycline of different types, and all these different types will be chemically modified in the R region. So if you see R1 on the top of this diagram, you will have R1, R2, R3 and R4. So when these regions are changed, you get various forms of tetracycline. So chemically it is 4-dimethyl amino, 1,4,4-A, 5,5-A, 6,11, 12-A, octohydro, 3,6,10, 12, 12-A, pentahydroxy, 6-methyl, 1,11, dioxo 2, naphthalene, carboxamide. So chemically they are 4-ring structure. So as I told you, this is a basic form of tetracycline. You have different types of tetracycline. Tetracycline, chlortetracycline, oxytetracycline, minocycline and doxycycline. If you see these R1, R2, R3 and R4 regions will have changes chemically. So producing strain is on the right hand side. Tetracyclines are produced from Streptomyces aureus, Streptomyces flavus and Streptomyces antibioticus. Chlortetracycline produced from Streptomyces aureofaciens, Streptomyces viridifaciens, Streptomyces flavus. Oxytetracycline produced from S. antibioticus, S. cellulosae, S. parvus and S. ramosus. Minocycline produced as a semi-synthetic form of any of these producing strain, and doxycycline in a similar way. All these strains could produce where chemically the R structures are modified. So again, biochemical pathway to synthesize chlortetracycline by Streptomyces aureofaciens. Glucose giving rise to pyruvate acetyl-CoA. Acetyl-CoA carboxylase converts acetyl-CoA to malonyl-CoA, and in malonyl-CoA you have a combination of what is called as oxaloacetate by oxidative decarboxylation. There is transamination where you form melanoyl CoAe. Of course, you have intermediate cyclization. Polyketide intermediates are formed, that is 4-ring structures. 6-methyl pretetramide are synthesized. Anhydrochlortetracycline produced. Dehydrochlortetracyclines are generated and of course is converted to chlortetracycline, which is produced by S. Streptomyces aureofaciens. So it is an outline of biosynthetic pathway of chlortetracycline by Streptomyces aureofaciens. If you look into all the phases or synthesis of these different antibiotics, the primary metabolic stage or primary cycles of its metabolic pathways are bypassed chemically to produce an secondary metabolites. So regarding the production medium for the production of tetracycline, it has to be supplied with carbon source, nitrogen source and minerals. Medium for the fermentative process of tetracycline production essentially comprises of carbon source, which is supplied in the form of glucose or starch, nitrogen source, the corn steep, liquid, soya flour or peanut meal, and mineral source is given with the help of sodium chloride or chlorine ions. I repeat, medium for growth or production medium. Medium for the fermentative process of tetracycline production essentially comprises of carbon source, glucose or starch, nitrogen source, corn steep, liquid, soy flour or peanut meal, and mineral source, sodium chloride or chlorine ions. Production process, you can use two different strains to produce tetracyclines. The production strains, Streptomyces aureofaciens and Streptomyces rimosus. Aerobic submerged fermentation is the method for production, which is a feedback fermentation. Temperature employed 27 degrees Celsius to 30 degrees Celsius, pH 6.5 to 7.5, aeration 0.8 to 1 vessel volume per minute. Duration of fermentation is 4 days. And regarding its recovery, filtrate is treated with N-butanol or methylisotbutyl ketone in acidic or alkaline condition for extracting the antibiotic. Then they are absorbed to activated charcoal to remove other impurities. I repeat the production process. The production strain, Streptomyces aureofaciens and Streptomyces rimosus. Aerobic submerged fermentation, fed batch fermentation, temperature 27 degrees Celsius to 30 degrees Celsius, pH 6.5 to 7.5, aeration 0.8 to 1 ppm, duration of fermentation is 4 days, recovery, filtrate is treated with N-butanol or methylisotbutyl ketone in acidic or alkaline condition for extracting the antibiotic, then absorbed to activated charcoal to remove other impurities. Of course, this chart will give you an outline of the production of chlor-tetracycline. The inoculation, the inoculum is the lyophilized spores. You are generating it with the help of agar plates. Shake flask is used in order to grow it in larger number. Pre-fermenter vessel to develop it. Fermentation, of course, fed batch mechanism. Mycelial removal, and of course recovery and purification of the product. So underneath, if you see, you have a flow chart, inoculum in agar plates, then to shake flask, then pre-fermentation or pre-fermentar, going back to fermentation, mycelium removal, and finally recovery and purification.